Hi, my name is Nick Grenci, and today I'm going to talk about Monte Carlo simulations for time-of-flight epithermal neutron activation analysis for isotopic signatures. So there is a need for a fast, non-destructive technique to monitor nuclear material throughout the fuel cycle, and epithermal neutrons can allow for more information to be extracted compared to a typical thermal activation analysis. So for example, the two plots on the bottom show cross-sections for different isotopes of plutonium for the end total interaction, and the plot on the left illustrates the thermal energies of isotopes 238, 239, 240, and 241, and over the thermal energy range, the cross sections do not vary much, and for the four different isotopes mentioned, they're within one order of magnitude and very similar at specific energies. Whereas in the epithermal energy region from 0.1 to 40 electron volts, for which this chopper is being designed, different resonance peaks can actually be distinguished and are multiple orders of magnitude difference between the isotopes. So this can actually allow for preferential activation of a specific isotope. So we're working on this project because there is a need for new tools and techniques to monitor nuclear material at various stages of the fuel cycle. Everything from mining and milling of uranium to conversion and fabrication of fresh fuel, the enrichment process, plutonium separation at reprocessing facilities. So this research is relevant to the NSA mission by complementing current state-of-the-art in the areas of signals and source terms for nuclear non-proliferation. So the way that we're approaching this problem is to develop a prompt and delayed gamma neutron activation analysis system based on both thermal and epithermal neutrons. So this will actually be able to provide the capability to perform epithermal neutron activation analysis, which can complement time-of-flight neutron transmission measurements. And this will help us in assessing elemental and isotopic signatures that are specific to nuclear fuel manufacturing processes. So to do this, we're developing a novel piston-based mechanical neutron chopper to create a source of nearly monochromatic epithermal neutrons. And this is advantageous because it will reduce the activation of unwanted nuclei from the full reactor spectrum, particularly thermal activation, where some of the resonances in the energy region of interest will be preferentially activated, which will give a better isotopic signal. So Monte Carlo simulations are being used to characterize this source of neutrons and quantify this novel chopper's utility for epithermal neutron activation analysis. So right now we're building simulation tools to optimize the mechanical chopper along with the experimental parameters. And the figure on the right shows a diagram of a slider crank mechanism, which is the way that this mechanical chopper will work, where the piston will actually contain a neutron absorbing material, and the bottom figure illustrates the dynamics of how this chopper will work. So the neutron source coming from the reactor will be collimated through the small slit in this piston, and this is a cross-sectional view of the Monte Carlo simulation of the actual piston itself, where we can think of the piston as moving up and down in relation to this view, and then these neutrons, once chopped twice, will be able to preferentially activate this target based on a specific resonant energy. So to characterize this source of neutrons coming from the Brazil reactor, we've been working on characterizing the beamport that it's intended for use for this mechanical neutron chopper. So the Penn State Brazil reactor has actually recently undergone renovations to include new beamports and a D2O tank, and these beamports are now directly coupled to the D2O tank, whereas in the last configuration, only one beamport was directly coupled to the D2O tank, and they had different levels of height in relation to the center of the reactor core. And now these new beamports all have the same height level directly centered at the center of the reactor core. So Monte Carlo simulations have been used to characterize beamport number 1, which is the one that we will be using for these experiments to fully define the neutron source with simulations. And this actually informs the design of the mechanical neutron chopper itself, as well as the filter and other experimental parameters. So the figure on the right illustrates the flux spectrum as a function of power of the reactor operating, and the way that this was determined was the criticality source from the Penn State Brazil MCMP model was converted to a fixed source, and through variance reduction techniques, we were able to efficiently simulate the neutron flux at the outlet of this beam port. And we can scale this into 3 energy groups: thermal, epithermal, and fast, as a function of power. In order to fully characterize the neutron flux in the beam port, simulations have been conducted to evaluate the flux spectrum at different locations of the beamline. And this is used not only to optimize the neutron activation analysis experimental parameters, but also to gauge the production of argon-41 in the beam port as the reactor is running from a health physics standpoint. So the figure on the right illustrates the neutron flux spectrum at 3 different locations within the beamline, and then 1 at the direct outlet of the beamline. And these fluxes were used to estimate the production of argon-41 at any given power level, along with irradiation time. So right now, for the gold foil experiments that we're planning to do first, with an irradiation time of approximately 20 minutes and 20 kilowatts, with the Beamport 1 being unplugged, it's estimated that there will be a small amount of argon-41 production at the end of this experiment, which is enough so that the Beamport will need to be covered with some sort of membrane to contain this argon-41. So along with the production of argon-41, the flux spectrum at the outlet of the beamline that will actually be used for the activation of different foils and wires has been used to calculate different doses, to estimate these doses, so that these experimental parameters are optimized for both safety and efficiency in running the reactor. So these simulations will be experimentally validated through a set of foil activation experiments, and this information will be plugged into a neutron spectrum unfolding software, STASEL. And as of now, the foils and wires that we plan to irradiate are broken into 3 categories. So the first is for the wires and sensitive that most sensitive to fast neutrons: indium, iron, titanium, nickel, magnesium, and gold, silver. And this will produce one set of reactions that are most sensitive to neutrons in the fast region. The second set of wires and foils will be sensitive to thermal neutrons, and this is indium, iron, copper, gold, cobalt, and tin. And the third set will actually cover the epithermal range, and these thermal foils and wires that were just mentioned that are most sensitive to thermal neutrons will be repeated with cadmium covers. So these figures on the right just illustrate the new configuration of the D2O tank and beam lines, and where the picture on the bottom is the open beam ports during renovation. So the far left opening is what is now Beamport 1. And in the top picture, Beamport 1 can be seen as the far most left beam port coupled to the D2O tank. So one tool that we're working on is an optimization tool for different experimental parameters, and this is based on the Monte Carlo simulations that we've been working on. So these results have actually been used to create a data set for the optimization of these activation experiments. So the following parameters were considered when building this tool. One is the allowable power level of the reactor for the unplugged beam port configuration. We assumed three group neutron flux and used the associated cross sections with bin fast flux or bin fast cross sections. It also had considerations for gamma and beta dose from the considered foil or wire. And this also took into account decay during irradiation, cooling, and counting times. And we assumed some parameters for detection efficiency and counting statistics, while also considering the argon-41 production based on power level and irradiation time. So using this information, we were able to construct a data set to pick the best set of parameters to not only get the sufficient counting statistics we needed, but to minimize dose and power level and irradiation time. So these simulation tools will ultimately be used to create a physical system to measure prompt and delayed gammas from activation analysis, and these will be used to complement neutron time of flight measurements. So time of flight measurements can be made to spatially resolve and identify isotopes in bulk samples. However, it may not be the best solution to identify trace impurities in a sample. So NAA is actually an analytical technique with very high sensitivities. So these two techniques can complement each other in this aspect. NAA is actually sensitive to parts per million or parts per billion. So this chopper system that we're designing can effectively monochromatize neutron pulses, which will allow for preferential activation of these trace impurities in a bulk sample. At the same time, it'll also mitigate the desired activation from thermal or off-resonant energies. So this will actually enhance the signal-to-noise ratio of the measured photons of interest to complement the time of flight measurements. Working on the MTV project has allowed for useful networking, particularly with experts in the field of interest, specifically time of flight measurements, mechanical velocity selection, and the nuclear fuel cycle, because this project is very interdisciplinary within the nuclear engineering field. And there actually is an interest from a national lab regarding this piston-based mechanical neutron chopper for designated use at a trigger reactor. And the chopper design is actually being aided by a professor of mechanical engineering at Penn State. So there's a couple different facets of this project that are ongoing. One is the filter design and optimization. So we're using Monte Carlo simulations to optimize a neutron filter that will be retrofitted at the end of Beamport 1. And this filter will be used to optimize the number of neutrons in the energy range of interest between 0.1 and 40 electron volts. And we're using a figure of merit to define the most optimal filter based on material and thickness. So we're actually creating an automation process to test different permutations of materials and thicknesses to maximize the intensity of neutrons in this energy range. And we've also assumed that neutrons below this energy range of interest are effectively removed by the chopper itself based on the neutron absorbed material contained within it. And this plot on the right illustrates a transmission spectrum from the full reactor energy spectrum being unfiltered to being filtered with up to 25 centimeters thickness of sapphire. Another area of work is time-dependent detector response. And so we're using Monte Carlo simulations to develop a time-dependent detector response to the cyclic neutron activation analysis. So this simulation tool actually utilizes the unfiltered neutron spectrum as a source for MCMP simulations. And it uses this instant on the neutron chopper itself. And this information is coupled with the kinematics of how the piston moves in time. And this is used to discretize time steps for neutron intensity, which then correspond to a specific detector response at an instance in time, with the chopper either fully closed, partially opened, or fully open to this neutron beam. And in doing this, we can simulate the prompt and delayed gamma response. And this will actually help us assess the utility of using different targets that we can select. We're also working on finalizing a mechanical design with the associated parameters of the physical neutron chopper itself. So as is, the stress state is very complex, so it will require a finite element analysis model before the chopper is actually constructed. And other things such as bearings, lubrication, and connections need to be evaluated in a more detailed fashion to determine the reliability and operational lifetime of this mechanical neutron chopper. So the next step for this is to actually create a very detailed CAD model with parameterized systems for easy iterations. So in conclusion, we are developing Monte Carlo simulation-based tools to analyze the quantitative performance of this piston-based mechanical neutron chopper for cyclic activation analysis. So we're modeling time-dependent detector responses, and the simulation tools will actually be able to quantify detector response to the undesired higher energy neutrons transmitted while the chopper is in the closed position. So these measurements will actually be used to complement time of flight measurements, such as transmission resonance analysis. So combining these two will allow for a fast, non-destructive, highly sensitive technique to analyze specific nuclear samples of interest. So this work does impact the NNSA mission by serving as a verification technique for nuclear material related activities. And I'd like to take this time to thank the NNSA and the Department of Energy for their continued support for this research activity.